Okay, now it's time for us to move on to the very different topic. In this chapter, we're going to study, per the title, is about the transformations of the plane stress and more circles. Basically, from here, this title is showing up to you as a beginners. There's a three keywords. One is transformation. Then the second one is plane stress. The third one is about more circle. And each of those terminologies are new, and I'm going to explain them in detail in the contents of this chapter here. So the outlines, basically here in these chapters, I'm going to have 5 little sections, and then based on the first one is about the transformations of the plane stress, in which 2 terminologies, transformation and the plane stress, is going to explain. Then the second one, we're going to talk about the principal stresses, and which is another terminologies, and the maximum strain stress, and that will give you a detailed plan, the detailed explanations. The third one is more circle, and then the more circles, apply the more circles method, and which is a very powerful method. I'm going to explain in detail in the fourth section. Then the section is about the pressure vessels, and that basically is the applications of those topics we learned here. So let's begin with the first sections, and let's talk about the transformations of the plane stress. And before doing this one, then let me give you the explanations and what is the transformations of the stress, and why do we want to transform this stress. Okay, so basically here is this is the given a given stress. Basically here we say the given status of stress. Okay, so basically the status of the stress, including here is we call the stress element. Okay, let's call the stress element. On the stress element that distributed is the 9 stress components. So each of those are called the stress component. Okay, in general, there's a 9 stress components, and then per our terminologies, if you remember, say tau xx, this one is the plane on which, for example, if this is the x-axis, let me change color here. So if this is the x-axis, this is the plane we call the x-plane, because the normal to this x-plane pointing to the x directions. So this plane, and which has a normal to z direction, so this is called the z-plane, okay, etc. So here the first component indicating which plane is lying to, so x, y, and x, z. So the 3 stress components are lying on the x-plane. So this is the tau xx, tau xy, and then this is tau xz. Okay. The second component indicating is the directions to which it's pointing to. For example, this one is in x-plane pointing to y direction, Okay, so basically this is a review about the description of the stress components in a given status of the stress, and then in terms of the stress element here. And so here for this given, basically it's given in a certain coordinate system. Here is x, y, z. And here about the transformation basically is this. If we would choose a different coordinate system, for example, x prime, y prime, z prime, and this is called a new coordinate system, respect to the original one, let me call it is old. And between the new and old coordinate systems, there existing some kind of the angle of transformations. Okay, so in this way, we want to describe what is the descriptions of the stress in terms of the new coordinate systems. So we want to describe the descriptions of the stress element in terms of the new coordinate system. And the new coordinate system basically or is in a certain transformation relation to the old one. So that is where this transformation coming from. That transformation is regarding the transformation between the two different coordinate systems. And each of the coordinate systems can be used to describe the stress element. So basically here we simply want to describe the transformation of the stress. Basically is to say you are asked to calculate or determine each of the stress elements in each of the coordinate system depends on which in specific you want you be asking. Okay, so basically here I define the transformation of the stress, and one more time in summary, the transformation of the stress is this: given a status of the stress and in say existing coordinate system, and also we are given a relations between the existing and the new coordinate systems, and that relation can be described by the rule of the transformations or can be described by the matrices of the transformation. Now the goal of the transformation of the stress is to find the description of the stress element in the new orientation. Okay, in such case prom. Okay. So that is the definition for this. Okay, so now then let me move on to what is the plane stress. Basically the plane stress is this. For example, in terms of the let me do this. So let me use this is called the stress element again. And again, this is in particular the three-dimensional stress element. And now let me designate the coordinate systems. For example, here let me follow this one. So this is the x, and using the right-hand rule, this is y, and this is z-axis. So basically, this is we call the x-plane. Okay, this is called the x-plane because it has the normal to the x directions. So this plane is called the z-plane. And this plane is called the y-plane. Okay, so we have the plane. Then let me define the elements. So in the x-plane we have three stress elements. So this is tau x in x-plane pointing to x direction, and this is in x-plane and pointing to y direction. This is in x-plane pointing to z directions. Okay, and you can move on. So in y-plane we have tau in y-plane pointing to y direction, and in y-plane pointing to x directions, in y-plane pointing to z direction. And finally, let me do one more. In the z-plane we have in z-plane pointing to z directions, and then in z-plane and pointing to x direction, in z-plane pointing to y direction. Okay, so that is the general. Here I describe is a general three-dimensional stress elements here. So now this is a basic three-dimensional stress element. Okay, basically the components of the stress basically distributed in three-dimensional. And now let me deal with a special case. A special case is such that if in certain situations or in certain applications, if you would find this, the green one are 0, basically all the elements in the z-plane become 0. Okay, so this one basically is tau z. So in this case, basically the element in one direction basically just being collapsed or 0. Under this case, this three-dimensional basically can be simplified as the two-dimensional. Okay, so simply you can see the green element, which is the components in the z-plane, basically under certain situations or specific application they are all 0. Under this situation we define as a plane stress. Okay, and in terms of plane stress, you can try to simplify the drawing. The drawing can be like this. Assuming you are the little guy sitting in the z-plane, and looking into the projection of the stress element in this viewpoint. So in front of you, you will see is this. In front of you, you will see this is x axis, y axis, and again in front of you, you will see this is tau xx, and this is tau yy, and this is the tau xy or tau yx. Okay, the same thing, symmetric here, here. Okay, so again, if you look at from this viewpoint here, then what you see is this one. So basically, this is a simple description of what we deal with for the spatial case when for the plane stress. Okay, so basically the plane stress, if you want to draw it in three-dimensional, is like this, but you can simplify the drawing by the two-dimensional like this one. So this one is our kind of the graphical representations for the plane stress being used again and again in this chapter. Okay, so that is the plane stress, and so that is the kind of recite what I just talk about that one. So this is three-dimensional and nothing special. For the plane stress, that means when say the z component, this one, and then this one, basically this is equal to 0, this is equal to 0, this is equal to 0. When the scenes 3, the stress elements in the z-plane become 0, then you can simplify the schematic drawing into this case. Okay. Now we talk about the basically here I'm going to have the first definition or the first taste of what is the principal stress and principal directions. When we back to the transformations of the stress. And again, here, let me remind you what is the transformations of the stress. Transformation of the stress is this. We are given a status of the stress. Okay, for example, like this one. A status of the stress basically is given, say, sigma x equal to how much, sigma y equal to how much, and tau xy equal to how much. And again, here we consider is the plane stress, okay? And also we are given coordinate systems. For example, xy. Okay, so the coordinate systems xy, the xy coordinate systems. And for the general transformation is this. We also select a particular angle theta. Okay, so for example, let me draw that one here. So this is x prime, and this is a y prime. So I pick a theta. The theta describes the relation between the new coordinate systems to the old coordinate system here. Okay, then we're going to find is this in the new transformed element. Let me enlarge this element. I don't want to mess up the drawing here. So here I kind of enlarge the schematically. So in these new orientations, we want to find is the new stress element. What is sigma x prime? What is the sigma y prime? And what is the element stress sigma x prime, y prime, etc. Okay, so that is sigma x prime and sigma y prime and tau x prime, y prime. Okay. So this is a general descriptions of the problem about the transformation of the stress. And now I want to talk about what is the principal stress. The principal stress is such that in the particular orientation theta, we call the theta p, in a particular angle or a particular value of the theta, in that particular orientations, the sigma tau x prime y prime becomes 0. Okay, so this is a very special conditions of the general stress transformations here, and this is so particular such that the shear stress in the transformed element becomes 0. In this case, we define such a particular value theta p is called the principal theta, or we simply call this is called the xy prime, called the principal orientations, or simply called the principal direction. And then the principal stress basically is to describe the normal stress element. So this is the maximum principal stress, and the other one should be the minimum principal stress. Okay, so in summary, what is the principal direction? In the principal directions, the shear stress component become 0. So this is such a very special orientation in which the shear stress becomes 0. And this has a profound meaning and applications. And we're going to see it when we have more understanding and the calculations of the transformation of the stress. Okay. Before we go to details, and this slide, and I like this slide, and this slide basically tells us why we want to learn to calculate the transformed stress, or why we want to learn the transformation of the stress, and why we want to determine the principal stresses, and why we want to determine the principal directions. Because once we have all the calculations and skills be learned, and then we can do the programming in the way we can try to trace the points throughout the structures like this one, and here those points, and the trace of the point become the curve that basically tell us is where is the maximum normal stress is, where is the maximum compressive or tensile stress is. And that one we can fit into the design criteria, and we can justify, okay, throughout the whole structure here, what is really the maximum stress? If we can ensure such a maximum stress is lower than or equal to the allowable stress, then the whole structures will be safe in terms of the design. So that, again, we back to our original design criteria. We simply want to make sure the structure is structurally safe. That means we want to make sure either the maximum normal stress is okay, that means under the allowable normal stress, or on the other side, we want to make sure the maximum shear stress is lower than or equal to the allowable shear stress. Again, this is back to our early chapter 1, the design considerations here. Okay, so sorry, let me get into this one. Okay, so that is a kind of big pictures and motivations and why we want to learn kind of the transformation of the stress, because simply, again, we want to have a very effective systematic way to help us to determine the maximum the stress component in whole structures. We simply want to learn a systematic way, hopefully, and you know how to do the programming and to scan through the whole structures of your design and to help you to determine these things. Okay, so now we come to the one step further. We go to the detail in more kind of the calculation details and about the transformation of the plane stress. Okay, so here in these chapters we dedicated to the plane stress, and of course once we learn these basic skills, we can extend it into the three-dimensional. But here we start from the simple one. So for the transformation is this. We are given this. So first one, we are given, you need to pick the coordinate system XY first. And about the XY, then you simply pick, this is a Y plane, this is an X plane. You simply take the X plane and Y plane and to form a stress element like this. On the stress element, you are given, or from the combined loading practice, you should be able to calculate what is the normal stress XY and the shear stress XY in terms of the coordinate systems. And here, okay, in terms of coordinate system, let me say this is lowercase, okay, to make that consistent. Okay, so that is a given situations. And one more thing, you are given, or you design, or you choose an angle theta. So you choose this angle theta such that you define this is our original coordinate systems, and our new coordinate systems is, let me call this as X prime, Y prime. Okay, so between that one, that angle is theta here. Okay, so in terms of the new coordinate systems, and you pick or I assign Then you pick up, this is the x prime plane, that is the normal to the x prime direction, and this is the y prime plane. Okay, using the x prime y prime plane, you form a stress element. On the new stress element, the distributed or the new stress element, and say this is the normal stress in x prime direction, and we use sigma x prime, and this is the normal stress in y prime directions, and then we define the sigma y prime, etc., tau x prime, y prime, tau x y prime. Okay, so we're going to find is we're going to calculate the three stress element. Okay, so we're going to determine the stress, the three stress, new stress elements. So that is our job to find it. Okay, so hopefully from here you know the definitions and what is the meaning of the transformation of the plane stress. Basically, this slides give us the given information and to find something. Okay. Before we do the detailed calculations, again, we need to pick up sign conventions. The first one is about the normal stress. So this is the sign convention for the normal stress, which is very simple. For tensile stress, positive. For compressive stress, negative. Okay, and now we come to the strain stress component. The strain stress components, you have two ways to memorize this. And let me show you the first way. The first way is I preferred the graphical way. So if you define the coordinate system xy like this, then this is the positive shearing. Okay, so in these orientations, and this is the positive shearing. And again, if you take the xy coordinate system like this, then this is the negative shearing. Okay, this is the way, and that can be memorized very quickly. If you like to go the other way, then we can take the symbols. So again, for the strain stress components, the first one indicating is the plane in which it's lying on. The second one is the directions. So for positive, basically positive plane, positive direction, that is a positive strain strain. Or negative plane, negative direction, then negative strain stress, the positive strain stress. Okay, so what is this? This one, you can, let me erase the information, sorry, and to get a better explanations here. Okay, for this strain stress, you can see if I define the xy coordinate system like this, so you can see this plane is the x plane. In particular, this is a positive x plane because this plane has the normal and out normal to the positive x direction. So this is a positive x plane. Okay, tau xy. So this is a positive, and also this strain stress component is pointing to the positive y direction. So this is a positive. So this is a positive. On the other side, let us take a look at this component here. So this plane, let me call this is the, again, this is the x plane. In particular, this is the outbounded normal pointing to the minus x direction. So that is a minus x plane. So this is tau xy, and this is in minus x plane, and you can see also the direction pointing to minus y directions. So basically it's a minus minus. So basically this one is also positive. Okay, so this is also positive, and this one is also positive. Okay, so basically that is the two cases. Then this case, let me change color here. So basically this case corresponding is this one. You can quickly check. This is positive x plane and pointing to negative y direction. So basically this is defined as a negative. Okay, then this case basically indicating is this component. You can from this moment you should be able to verify by yourself. So this is the sign convention for stress element. Now the sign convention for the angle, which means the transformation angle, and we define the positive is counterclockwise, and we define the clockwise as a negative. Okay, very easy. Okay, so for this case, this should be positive per our sign convention here. Okay, And one more thing, and since we have shown here, so one more thing before we go, and I want to give you these things here. And usually is this, when we do the analysis, we first pick up our coordinate systems, and then based upon the coordinate systems, we pick our stress element. And around the stress element, then we say using the combined loading skills, we should be able to determine the magnitude of the stress element, for example, like this, okay? So we should be able to determine the magnitude for the stress element. And from this moment onwards, then we begin to do the transformations. Transformation basically here is this: you pick the angle theta about which do you define the new coordinate system x1, y prime. Okay, so and now we know we're going to, the next step is to say using the this is the y prime plane, this is the x prime plane, okay? Then this is the transformed stress element, so let me highlight here, okay? Very messy, so that is the point I want to make. So you can see if here we overlap our transformed stress element to the original stress element, and along which we're going to calculate the stress element in the transformed orientation, something like this one. You can see the drawing right now I'm being made is very messy, because simply is we overlap information all together at the same place, and that's supposed to be like this. However, it's not good for our visualization of our calculation. So the quick solutions, and basically that is the common well-accepted exercise, is this: why not we simply artificially, okay, keep this in mind, we do it on purpose artificially, but suppose not to do this. We do this is for graphical simplification of our easy, make our things easy. So we're going to do is this: we simply offset the transformed element into other way. For example, like this. Here we offset our transformed element away from here to here. Again, this offset simply is to allow us with the easy visualization. But keep in mind, when we do this kind of offset, is do this on purpose. But you keep in mind the origin of the transformed, the new coordinate system x prime, y prime. This origin is supposed to be aligned to here, original here. Suppose this is the system we're going to deal with. For the transformation of the stress, we don't do rigid body translation. We only do the rotation of the coordinate system. However, to allow us with easy visualizations, we simply offset the transformed element away from the original one. Again, that is to allow the people to easily see the description. Okay, so keep this in mind. So now we talk about the techniques about the transformation of the plane stress, and which is very easy, and that is based upon the equilibrium equation, static equilibrium. So for example, if say you like to determine the transformations in terms of the x prime, y prime. For example, you are asked, I give you a number theta, for example, 30 degrees, counterclockwise. I ask you to determine the stress element in the x prime and in the y prime directions. Okay, so in this case, you simply you can do is this. And for example, you can pick from the original given stress element, you can pick this orientation. This orientation simply is to parallel y prime, or this orientation simply is normal to x prime. So from this one, you pick the triangular area, and let me highlight here. This triangular area is a portion of the given stress element. So this plane, okay, let me highlight, this plane is our x prime plane, in which we have two stress elements, normal stress element sigma x prime and tau x prime y prime. We calculated two. Once we done this process, then we simply choose another orientations. we simply choose a different one. Okay, so we repeat the same process, and in this way we can expose the sigma y prime and then y prime and then sigma x prime. Okay, so let us focus on this one. So in this element here, right now let's do the calculation carefully. So for this triangular element, and we have the distribution of the stress, and on this side we have the stress basically picking up from here. This is our original x plane, so we have the normal stress sigma x from here. We have the strain stress that is from here. Okay, and also from the bottom side, that is the our original y prime, our original y plane. In this y plane we have the normal stress, and that one is from this component. We have the strain stress, and which is from this component here. Okay, so this one is about the distribution of the stress. Now, and we on the other identical triangular portions, let it describe the area. For example, let me assume the sided area equal to A. Okay, and then in this way the area on this side should be A times cosine theta. The area on the bottom side should be equal to A times sine theta. Okay, basically that is proportional, assuming the out of the board dimension the same, don't change. So basically the area have in relation like this. So correspondingly, we multiply the stress elements, each stress with the area that will give us the force. Okay, for example, this stress element multiply the area it acting on, multiply with this one, that will be the force. So that is a force component like this. And then again, this is the stress element multiplied with corresponding area, and that is a force. Okay, in the similar way, this is the stress multiplied with this area, because right now this stress is acting on this plane. So that has the area like this. So that is this is a force. And in the way this multiplied with this area, which is this one, that is a force. Okay. So here we have the force component. In total, we have 4 force components. Those force components are in the original x and y directions. And now we're going to find the stress element sigma x prime acting on this plane. This plane has area A, so sigma x prime times A, and that is the force. Okay, and tau x prime y prime times the area A, so that is this force. Okay, so for some reasons here I use delta A. So here I use delta A. I should suppose use delta A here. Okay, so but anyhow. So here is the 4 force. Here is 4 known force components, because here these are given, this given, this given. So those 4 are known. And then we're looking for, and these are 2 unknown force components. Okay, so now in this way we simply take the equilibrium equations. So say the force in x prime direction equal to 0, and the force in y prime direction equal to 0. We'll simply take the force equilibrium in x prime direction in y prime directions, and you simply do the careful projections. For example, of this force component into the x prime y prime, let me do this one here. So you draw it. Okay, so that is a component in y prime, this is a component in x prime. And let me do this one here. So you project into this one here. So this is the component in x prime, this is a component in y prime, etc. Okay, so you do this one very carefully, one by one, and be patient. Okay, so now we should have all the calculation can be done. So here is a simple example here. So for example, here we are given this one, okay, and I ask you to determine the magnitude of the stress in this plane. Okay, in this plane. So you can do is this, you simply pick this element and expose something like this one here. Okay, And in this element, you simply copy the given stress. So this is the 60. So this is a 60 and this is 90 here, and then here is 90, okay, from here, and there's a normal stress here. So this is about the stress, and then the area, for example, you assume this is A, then this should be A sine 30 and this is A cosine 30. And then this is about the area, and then you multiply the corresponding stress to the corresponding area, then you will obtain the distribution of the force. For example, this is the stress element multiply corresponding area on which is acting on. So sigma times A give to this, and tau multiplied with A give to this. Okay, and then from the given informations, 60 multiplied with this area A30, so that is this one, and this component 90 multiplied with this one, that obtain this one, and then this component multiplied with this area equal to this one. Okay, so in this case we have two unknowns, and what two unknowns is, we have this one sigma and we have the tau. We're going to determine sigma and tau. Okay, so two unknowns. So we have two unknowns. You simply formulate the force in two directions. So let me say this is this direction. Okay, so you formulate the force in that direction equal to 0, and also you formulate the force in these directions. Okay, and equal to 0, and detailed calculation is like this. So two equilibrium equations allow us to solve for the two unknowns, so that if your calculation is correct, and do this patiently, and you should get this answer. Good? Okay, so that is a very simple illustration. We should be able to repeat this process and to determine the stress, and that stress basically is the stress in the new orientations. So from here, this moment onward, we can do general symbolic calculations. Symbolic calculation will allow us to lead to a useful formulas, and we call the transformation of the plane, the equations for transformation of the plane stress. Okay, so again, here we do all the symbolic calculation in terms of the symbols here. Those are the given, and we're going to find what is this and what is this. Okay, so simply proceed by repeating the same process, but in terms of the symbols. Everything all here are symbols. Then we come up with the very important equations. There's three equations here. So by following this equation, we should be able to determine the stress element in the new orientations. Okay, so basically that means is this. So we are given this. Let me do it in terms of symbols here. So we are given in terms of our xy coordinate systems, we are sigma x and sigma y. Sorry, this is a sigma y. And we have the stress, strain stress, tau xy. And then we're going to determine, again, you see I'm going to use the symbols. Okay, so here, for example, this is theta here. So in the new orientation, x prime and y prime here. So this is sigma x prime and sigma y prime, and then sigma tau x prime y prime, etc. Okay, I'm out of the space here for drawing. So basically here we are given this information, and we pick a value, then we're going to calculate the three stress components, and which are given in this equation here. Again, in this equation you need to apply the sign convention. You need to apply the sign conventions for all the stress. Okay, sigma x, sigma y, and tau xy, and sigma x prime, tau y prime, tau x prime, y prime, and also you need to apply sign convention for theta. Okay, and make sure the sign conventions are applied correctly. Otherwise, you will make a big mistake in your calculation. Again, sign conventions should be applied to those equations here. The second note is this: if you multiply the two equations, this one you add it up together, then you should be able to find this relation quickly. So that means the summations of the normal stress component are constant. Doesn't matter which orientation or which theta you work on, they must be constant. This is a very good property. We call this stress invariance, the principle of the stress invariance. Okay, so keep this in mind. This will provide you a check. You can apply this simply rule to check whether your calculation is correct. This is a very powerful property. Try to keep in mind. So again, this page we formulate the problem description. We are given these conditions. In terms of the XY coordinate systems, we are given, or you have calculated the stress component, okay? Then we pick theta. We want to determine the stress element, okay? This is the formula here, okay? So basically here, this is the graphical representation. Again, I extended. Suppose the two, this origin must overlap, must be at the same location here. But to allow the easy visualization, I kind of offset the transformed information from the original one for easy visualization. Again, this is a very common practice, okay? In terms of the three-dimensional view, you should be able to see it like this. Again, you are the little person, you're looking into this direction in front of you, or projecting to you is the two-dimensional view, something like this one, okay? And this is a general three-dimensional plotting of the plane stress, but again, two-dimensional graphics should be sufficient. So that, again, this is a repeat of the transformed stress elements kind of equations for you to pick up. Okay, so those are the notes, and we've seen this, okay? That is called the transformation equations. And again, the we call the normal stress invariance. That means the summation of the normal stress components must be the same. Doesn't matter which theta you work on. And for this case, this is called the uniaxial stress, which means we only have one normal stress in one direction. We call the uniaxial. Uni, that means only one in the x, in certain x, the axial, the axis directions here. Okay, and this is called the pure shearing, because here we only have a shearing component, we don't have the normal stress. Okay, so that is a very simple kind of the conditions. So this lets us look at the example here. So we are given this element. So from here we don't have any coordinate systems. Maybe I prefer you to keep a good exercise. You simply define the coordinate system XY like this. Okay. On the other side, if say I don't like this definition, can I do the definition of the coordinate system like this? Let me do say here. Say I like to define my XY like this. Yes, you can do this. As long as once you define your definition of the coordinate system, and then keep everything per your definition of the coordinate system, keep everything consistent throughout all your calculation, then your final result should be the same with other people. Okay, so it's okay if you define and keep in mind using right-hand rule. Using right-hand rule to define your coordinate systems. Okay, so I think the normal people like usually define the coordinate system like this. Okay, so let me pick this one. So now we simply want to say the theta equal to 25 degrees clockwise again, and that will be per our sign convention is negative. Okay, so this one, the problem B, 10 degrees clockwise, so counterclockwise, so that's a positive here. And for the given stress element here, you can see this is the normal stress compressive. So we have the normal stress negative, and sigma y is tensile, so sigma y is 90, and tau xy given this orientation per our definition of xy I define here, so this is positive. Again, this is positive per my definition of the coordinate systems. If you choose a different one, then that could be negative, but again, keep everything consistent with your calculation, with your definition. Okay, so that is a given information, then you simply plug it here. So you can see from the right hand side of the three equations, those are the defined already. So you simply do the calculations. Okay, so you do the calculation, these are the results quickly provided to you. So again, this one we simply exercise is this how to apply the equations to determine the transformed stress element. Okay, that's called the transformed stress element. Okay, so simply in the first sections, we simply apply these equations. And again, if you like to do the programming, you can quickly program the three equations, and then you just input all the stress element everywhere throughout your design. You can quickly get a very good information and the sense about the design, your design. Okay, so that is for this is the answers, and that is for these sections.